All right, starting from the current slide. Couple of announcements before we get started. First, I wish someone was here, but no one's in the room but me right now. But we got to get student course evaluations done, okay? What they're aiming for, the dean has said, somebody has said, they want us to have at least 80% participation in student course evaluations. With this class, if one of you do it, we got 50%. We got to need both of you to do it to get 100%. So please, folks, both of you, please do your student course evaluations. You don't have to do it right now if you don't want to. If you want to wait and see, what you do on the next test or the final or something like that, that's fine. But please don't forget it. I know that when I was an undergraduate, once I took that last final exam, I was mentally on the way home. Okay, I was not thinking about anything else, so I would not have put off. We used to have to do ours in class the last week before classes, but they give you more options now. But please don't put it off indefinitely. Please do it, because they will close it out and then you won't be able to do it and we don't get our percentages up. So please do your student course evaluations. If you have any questions of how to do that, please see me. Okay? Now, the other announcement is not as important as that one, but it is just to let you know. I normally have office hours on Fridays on the Birmingham campus from 7:45 to 11:45. Not this Friday. I've got an infusion coming up this Friday. I will have to be at the correctional clinic before 7 and probably will be there after 4. So there's no way I'll be on the Birmingham campus this Friday at all. So no office hours this Friday. So don't come looking for me Friday. I won't be there. All right. That said, let's move on to, again, I wish someone were here. I'd like to ask if there are any questions. We are in Chapter 4, which is vector spaces, and 4.1 is vectors in Rn. And that is exactly what the title of this subsection is, vectors in Rn, top of page 149. The discussion of vectors in a plane can be extended to the discussion of vectors in n-space. Certainly in 3-space, that makes sense. N-space is harder to see. If n's anything greater than 3, it's hard to see. But just picture it as an ordered n-tuple. That means you have n dimensions, you might say, of it in entries of your vector. N components, I guess is the best word to say, of the vector. An ordered n-tuple represents a vector in n-space. For example, an ordered triple has a form of x1, y1, x1, y, x2, x3. An ordered quadruple would be of the form x1, x2, x3, x4, and so on up to an n-tuple would be x of 1, x2, x of 3, dot, 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 all the way up to x of n. Sorry. I don't know what's going on. Y'all have suffered through me suffering through stuff all term, but today has been so bizarre. I didn't have any sign of any problems this morning, last night, driving in, nothing. Everything was just sort of normal. And I taught my first class, and about halfway through my first class, suddenly I just got into a sneezing fit. And I just sneezed and sneezed and sneezed. And then that opened up my head, and my nose just started running like crazy, and I could hardly get it to stop. Okay? In between my first and second class, I went down the hall, I went to my office, I did things. Not a single sneeze after that. None. Nothing. Came back for my second class, and within 15 minutes I was sneezing like crazy again. Then in between the second and third class, this class, I went down the hall, went to my office, I spent more time out, not a single sneeze, no drainage, nothing. I come back into the classroom, and now what, just less than 5 minutes into the class, I'm sneezing again. I don't know what's going on. I don't know if some student wore something this morning that I'm allergic to, and it took about half a class for me to start, and now every time I come back in the room, I don't know. I don't know what it is. Okay. All right. So let's move on. Sorry about the break. Okay. And by the way, the set of n tuples is called n space of all n tuples, and is denoted by Rn. It's not registered nurse. It's R superscript n. Okay? So the R1, as they show in the book, is the set of all real numbers. You would represent that graphically by a straight line. Okay? R2 would be the plane. Set of all ordered pairs of real number. That's called 2 space. That would be like the board, the floor, the ceiling, a wall. It would be any plane. That's R2, two-dimensional space. R3 would be space, as we know it, That would be length, width, and height, okay? 3 space, 3 set of all ordered triples of real numbers. And then from there on, it gets somewhat abstract because I can't picture it or describe it or anything else. R sub n would be n space, set of all ordered n tuples of real numbers. Now, notice there the word ordered is always in there, okay, because the order matters, okay, and there has to be either 2, a pair, triples, n tuples, whatever. Now, an n tuple, they're going to write it here, and I'll write it down for you too. X sub 1, X sub 2, X sub 3, comma, dot, 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 comma, X sub n. So you have n of those things. That can be viewed as a point in Rn with all the x sub i's as coordinates, or you can represent that or think of that as a vector x in Rn, and each of these are now components. Now, I think I've mentioned this before. This author, in his earlier text and other texts that I've taught from, always indicates vectors by an angle bracket, not parentheses. In this book, however, he represents points and vectors with the same symbology, parentheses. So you have to pick it up from the context, whether he's talking about a point in n space, which would be the top one there, or it would be the vector in n space, which would be the second one there. Okay? So you just have to get it from context. And each of those are now components with a point. Those are coordinates. Okay. Now, let's talk a little bit more about vectors. As with vectors in the plane, which is R2, I'm so glad you're here. Yes. Yeah, thank you. Wacko talking to myself. Let me turn on the projector. And let me warn you now, hopefully it won't happen, but it has the first two classes today. This morning, last night, no time did I have any drainage, sneezing, anything. Felt perfectly fine until this morning. About midway through my first class, I just got to sneezing. I couldn't quit sneezing. And of course, once the sneezing stopped, everything in my head started draining. Okay, and I have been, that's why I sound probably somewhat stuffed up, because I am stuffed up. And I don't know where it came from. After the first class was over, I went out in the hall, I went out to my office. As soon as I got out of the classroom, I never had sneezed again. No more drainage, except what was residual, you know. It was bizarre. And then came back in here, taught my second class, and not that time, not more than 15 minutes into the class, I was sneezing like crazy again. And then drainage like crazy. I actually had to stop and go to the restroom to clear my head one time, because it was just too much to stay in here. And then, in between that class and this class, I went out in the hall, down to my office, everywhere. Didn't sneeze, didn't have any more drainage until I came back in, and 5 minutes into this class, I started sneezing again. So I don't know. I don't know if a student wore something I'm allergic to this morning, and it took me halfway through the first class to get to me, and now it continues in the room. I don't know. It's just as bizarre. All right. So here we are. We're on page 149, chapter 4, vector spaces. 4.1 is vectors in Rn, and that's the title of the subsection we're in now. Okay, we're just talking about that. This book is symbology here. And I've used this author in soon to be 3 other texts. Well, 2 other texts, 3 other courses. And in every one of them, he uses an angle bracket when he's representing a vector, parentheses when he's representing a point. In this book, he doesn't. Same author, but he uses this as symbology. So the top one can be a point. This one is a vector, because it's listed as vector. Okay. The first is just a point. Okay. And it looks the same. So you just have to pick it up from context what he's talking about. Sorry. Now, with that said, let's now talk about vectors. As with vectors in the plane, which is R2, 2 space, 2 vectors in Rn are equal if and only if the corresponding components are identically equal. Okay? So, if this is vector x, and then you had a vector y, which was y1, y2, y3, up to y sub n, same space, every one of those components must be identical. You can't change the order, you can't change anything about them, they have to be absolutely the same. And if they are, then the 2 vectors are equal. Okay? Okay. Now, the other little thing they note here, when they're talking about n space, meaning n greater than 3, we usually use, if this is vector A, like I just said, vector x, we name all the components, x1, x2, x3. Vector u would be u1, u2, u3, yeah, up to un. Vector v would be v1, v2, v3, v4, up to vn. You know, we would do that when we name it. When you're in 1 and 2 space or 3 space, we usually do xy or xyz. Means the same thing, but usually we're used to calling those by the coordinate names. You don't have to. Okay. Now, let's talk about the sum of 2 vectors in Rn, and also the scalar multiple of 2 vectors in Rn. These are called the standard operations in Rn, in any space, no matter what size n is, and they're defined this way. Well, that's not what I wanted. Let me erase all the ink here. So, here's a definition for vector addition and scalar multiplication in Rn. Just like you would expect, I hope. Let U That's their favorite name for a vector. Now this time, and remember the last time I think we were in here, I said U is not always a unit vector. Don't assume that it is. This one's definitely not a unit vector, necessarily. It could be, but it doesn't have to be. So in our standard convention, we're going to call the components U1, U2, U3, all the way up to and including U sub n. Okay, there's your vector in space, vector U in n space. You also have vector V in n space, and that will be V1, V2, V3, dot, 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 up to and including V sub n. Two vectors in n space, okay? Both in Rn, that's the other way to refer to n space. Okay. And it's almost redundant because if they have n components, sorry. Sorry. If they have n components, both of them are obviously in Rn. If they didn't have n components, they wouldn't be in Rn. If they had more than n components, they'd be Rn plus whatever. If they had fewer, they'd be in Rn minus one, whatever. So these are in n space. Same number of components. Okay? And we're also going to let C be any real number. Okay. Then the sum of U and V, U plus V, you can add them. Here's why you can add them. They have the same number of components. They're in the same space. So the sum of U plus V would then be, quite precisely, U1 plus V1, comma, U2 plus V2, comma, U3 plus V3, comma, dot, 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 comma, all the way up to U sub n plus V sub n. That's how you add vectors in n space. Add them component by component, just like we did in R2 and R3, and every way we've done it up to now. You just add each one. So that's vector addition in n space, Rn. Sorry. Man, it just starts and it won't stop. Okay. Man. So that's vector addition. Scalar multiplication of U by C is this. C times U would be the vector CU1, comma, CU2, comma, CU3, comma, dot, 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 all the way up to and including CU sub n. Okay, n components there. Every one of the original components of U is multiplied by that scalar C. All right. Now, that's the only two definitions you have to know, but just like before, these lead to other things that are useful to know and use. I'm sorry. Yuck. Okay. As in 2 space and 3 space, the negative of vector in Rn, so let's say you had a negative U in Rn, it would be negative U1, comma, negative U2, comma, negative U3, comma, negative dot, 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 comma, negative U sub n. Okay, you negate every component. Now, understand, that doesn't mean all these are negative numbers. Because your original components, remember, they can be any real number. So any of those components could be positive, negative, fractions, zero, decimals, it doesn't matter. Rational, irrational, it doesn't matter. They're just numbers. But whatever those numbers are, you negate that number. If that was if u sub 7 was a negative 14, then the negative u, its seventh component, would be positive 14. You just negate whatever the previous one was. Okay? All right. Now, another definition that we use is subtraction, or the difference in two vectors. So if you had u minus vector v, we don't need to come up with a new definition here. This is merely, taking the vector u and adding to it the opposite of v. Okay? And guess what? That's exactly how we add or subtract signed numbers, right? If you're subtracting signed numbers, you take the first one, then add the opposite of the second one. Same thing here. Add the opposite. That's how you subtract vectors. All right. Now, one more, and it's the zero vector. Okay? Every space, vector space, has a zero vector. So if you're in Rn, then the zero vector in Rn would be component 0, 0, 0, dot, 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 comma, 0, and you would have to have n of those zeros. Okay? Now this is the vector 0, the zero vector in that n space. The zeros inside there are scalars. So this is probably the only time, that I will take a number and put an arrow over it, because you have to distinguish the number 0 from the zero vector. Okay? All other vectors you can name whatever you want to, and you can name this one too, but you couldn't tell it's a zero vector. So they usually use in the book a bold 0, and since I can't write bold, I put the arrow over it. Okay. Yes. Okay. Okay. Now there is a little blurb on the left margin that's under technology. It says many graphing utilities and software programs can perform vector addition and scalar multiplication. If you use a graphing utility, then you may verify example 4b, which we haven't done yet, and I'll let you take a look at that. I don't have a graphing utility, so if you got one, follow that. Okay, so let's do example 4. Oh, man. Here we're doing vector operations in R3. Here's U in R3 space. Components are -1, 0, 1. Now, just because that's your exact, well, you'll see it on the next one. Vector V, also in R3, is 2, -1, 5. Okay. I was a little concerned when they gave that first one. I didn't want you to ever think that they have to be increasing in order and size. -1 is less than 0 is less than 1. They don't. Like the second one, V there, is 2, -1, 5. 2 is greater than -1, but -1 is less than 5. So yeah, they can be any numbers. These are both in R3 because they have 3 components. That's the dead giveaway there. Find each of the following vectors. Let's first do U plus V. Can you tell me what that vector would be? 1, comma, -1, comma, 6. Is that what you said? Yeah, perfect. Second, the B part says find 2u, as in happy birthday. Okay? What would that be? Second, 2. Yeah, okay. And the third one here is V minus 2u. Yeah, 4 because it's 2 minus 2 times minus 1, which would be plus 2. That would be 4. Got it? Negative 1. Got it? 3. Excellent. Okay? 4, 1, negative 1, 3. Brr. I feel so rotten. Okay. Yeah, they got the right answers too. I was just checking to make sure I hadn't either misread or misunderstood. There are some other properties we're going to talk about. We talked about the two, and by the way, those, the vector addition and scalar multiplication, interesting they have this name in light of what the title of the course is. Those are the linear operations. That's what shows. Goodness gracious. That proves linearity, and we haven't even defined that yet. But the following properties of vector addition and scalar multiplication for vectors of Rn are similar to those listed back in Table 4.1 for vectors in R2, then the proofs based on definitions of vector addition and scalar multiplication in Rn are left as an exercise in exercise 58, which is even. We're not going to do it unless you want to, and you certainly can. So here are additional properties of vector addition and scalar multiplication in Rn. These don't replace the other two, they're just in addition to the other two. Okay. And here your givens are U, V, and W are all vectors in R3, I think it is. No, Rn. C and D constants. Okay. They call them scalars. Okay. All right, the first of these. I'm sorry. I need to go clear my head again. I hate this. Okay. These are the properties. If you have two vectors in Rn and you add them together, okay, then that sum is also a vector in Rn. Okay? In other words, adding two vectors together may expand the vectors, make them bigger or smaller, by the way, but they stay in the same space. They can't go to another dimensional space because they're both in Rn. The sum is on Rn. That's called the closure rule, that they're closed under addition. Okay. Oh, I forgot to turn it back on. Sorry. Oh, man. Okay. All right. It's coming back up. And by the way, real numbers are this way. Any two real numbers you have, add them together, you're going to get another real number. Okay? Integers are that way. Add any two integers, you're going to get an integer. Okay? Whole numbers are that way. Rational numbers are that way. just by all of our sets. However, if you had the set of numbers 1, 2, 3, 4, 5, that set is not closed under addition because 4 plus 5 is 9. 9 is not in the set. Okay, so it has to be. The same thing is true of spaces. Okay, so here's another one. Number 2. Sorry. Okay. Thank you. This is how it started this morning. Just suddenly, a fit of sneezing. And then the flow starts. Okay. Yuck. All right. The second of these is if you have two vectors in Rn, u plus v, that's the same as v plus u. We did this in R2. Don't know if we did it in R3, but it's true for any Rn. If these two vectors are in Rn and you add them together, it doesn't matter what order you add them. And this is called the commutative rule of addition, commutative property. Okay, commutative property of addition. This is probably not a very good way to remember, but it's how I remember. If I commute from home to here to come to work this morning, we call that a commute. And then I go home by the same route, even though I'm going in the opposite direction, it doesn't matter. I go the same distance. Now that's if I go the same route. Okay. So u plus v is the same as v plus u. All right. Now, number 3. If you have the three vectors, u plus v, and you add those two together and then add that to vector w, these are all in the same space, vector space, that's the same as adding u to the sum of v plus w. And that's the associative property of addition. Okay? Now, the fourth one is a fairly straightforward one. Hopefully you'll see that if you have vector u and you add it to the 0 vector in that same space, so 0 vector must also be in Rn. That means you have you have n components of 0 in that vector. This is always equal to the vector u. Okay? Because to every component in u1, you're adding 0. That's still u1. To u2, you're adding 0. That's still u2. To u3, you're adding 0. That's still u3. All of them add up to be 0 added to any number is still that number. Okay? So that is the additive identity property. Additive identity property. Number 5. If you add to vector u the opposite of u, you're going to get the 0 vector every time. No matter what space you're in, you're going to get that size 0 vector. And that's the additive inverse property. Okay. Tell you what, this feels like a full-fledged cold. And it just started out of nowhere. and blossomed into this in a matter of just a few minutes. I've always either felt bad or something beforehand. There was nothing. It just came. Okay. I hope it's not a cold, but it may be. What's that? Okay. Yeah, they certainly are. I don't know what's making them drain, but they certainly are doing that. All right. Those are all additive things. But beginning at 6, we're going to start doing some multiplicative things. For instance, that CU, remember, we did that before. That's the scalar multiplication. But if you multiply a scalar by a vector in Rn, then the product of C times U is also in Rn. And that's the closure under scalar multiplication. Now, what they say is closure. Oh, no, they say it right. Okay, good. Occasionally, sometimes they won't specify. They'll just say multiplication. And there's like 3 kinds of multiplication of vectors. Scalar multiplication, dot products, and cross products. So I don't like just to say multiplication. I like to specify which multiplication it is. This is scalar multiplication, for sure. Okay, I can't. This is bugging me because it's flopping around on me too much. Okay. Number 7 is C times U plus V is the same as CU plus CV. And basically what that's saying to you is that scalar multiplication distributes over vector addition. And this is where they leave off the terms. They just say distributive property. But I like to call it scalar multiplication distributes over vector addition. Okay. Yuck. All right. Now, number 8 is almost the reverse of that. This time you're going to start with 2 scalars, C plus D, and multiply those by vector U, I believe it is. Yeah. Doesn't matter which one. I just wanted to be consistent with the book. That's the same as CU plus DU. Okay? Now that's another form of distributive property, but this is, I guess, vector multiplication across scalar addition. Okay. In other words, they sort of go both ways. Number 9. Now this is as close as you can get to an associative property. If you have a scalar multiplied by a scalar times a vector, that's the same as the product of 2 scalars, CD, times a vector U. Okay? So that is, yuck. They just call it associative property of multiplication, but it's associative property of 2 scalars with 1 vector.
Okay. I don't know if you can read my writing. What's happening now, whenever I get very much written on a slide, the pen slows down and I can't see what I'm moving the pen across the page, but nothing is showing up, so I don't know how my spacing or anything else is looking until after I'm through writing. Then finally the pen catches up, and sometimes it's not very pretty. Okay, and then here's the last one so far. 1 times the vector u is equal to the vector u. Okay, and that almost comes directly from your scalar multiplication. That c times u is cu1, comma cu2, comma cu3, comma cu4. Here your scalar is 1. So 1 times u1 is u1. 1 times u2 is u2. 1 times u3 is u3. So you get the vector u all over again. And that's the multiplicative identity property. Okay. Now, before we move on, there's a little blurb on the left side margin of this page on William Rowan Hamilton, considered to be Ireland's most famous mathematician. In 1828, he published an impressive work on entitled A Theory of Systems and Arrays. In it, Hamilton included some of his own methods of working with systems of linear equations. He also introduced the notion that of the characteristic equation of dimensions. I'm not going to do it anymore. You can read that on your own. I was just going to see if there's anything that might lead itself to a paper topic. I guess just writing about Hamilton, but you've already, I think both of you have already turned in your paper, so not much more. But he was a very powerful mathematician way back in the early 1800s. If I'm not mistaken, now I may be wrong on this, but quantum mechanics, which didn't come into existence until sometime early in the 1900s, I think uses some of his mathematical symbology because they use what they call the Hamiltonian, which is an operator that is a bizarre type operator. You can do so many things with it, and its name is the Hamiltonian. He's the only Hamilton that I can think of that that could have been named after. There could have been others, but he's the only one that I know of, and he was almost a century ahead of the people who were going to use some of his symbology. So it's pretty impressive how far he pushed things along. Okay. Now, I'm sorry, I'm having trouble breathing. It says, using these 10 properties from this theorem, this is theorem 4.2, says you can perform algebraic manipulation with vectors in Rn in much the same way as you do real numbers are demonstrated, as demonstrated in the next example. But before we move on from there, let me point out some differences here. We keep saying how similar it is to real numbers, but here are some differences. Notice all these things with addition are true. Closure, commutative property, associative property. They didn't mention, but the distributive property, at least some forms of it, are true. Okay? Now, when you got into multiplication, closure was certainly there. Okay? And then, like I said, a few of your distributive
type things, a few of your associative type things, but notice you have to have almost a plethora of constants, scalars there. Because, and this goes with what I said before, there's three types of multiplication when you're dealing with vectors. Scalar multiplication fits the pattern nicely. But when you get into vector multiplication, which is two kinds, dot products and cross products, no. You can't set these things down like that. Notice there is no commutative property of multiplication, not of vectors, okay? You could do C times U is the same as U times C, but that's just sort of nebulous, okay? But they didn't even list that. They did a associative property down here, but it had to be, two of those entities had to be scalars and only one a vector, because you just don't define vector multiplication easily. In fact, there's two different kinds, and it would be hard to come up with these properties in that. So, yeah, there's a lot of similarities in your properties of real numbers, but there are some differences as well. Okay. Oh, man. I hope to make it through without having to stop again. I'm about to fill up my next one. But let's see if we can move on. Let's do example 5. So let me erase the ink. All right. Here we have some vectors. Here's vector U, 2, -1, 5, and 0. Okay? Here's vector V, 4, 3, 1, -1. Okay? Here's vector W, -6, 2, 0, 3. Okay. Now, what space are these vectors in? Second? No, 4. Four components, so they're in 4 space. R4, R superscript 4. So they are in R4. These vectors are all in R4. How many components they have? Okay. And it says find x, vector x, using each equation. Vector x. Well, the first vector x here is 2u, as in happy birthday, minus v plus 3w. All right. Now, there's a bunch of ways you can do this. You probably technically should use your rules of order of operation strictly, but as long as you don't violate any of them, you can adjust them a little bit. Like, it's real easy just to go on and do what 2u is. Let's write that first. What is 2u? 4, -2, 10, 0. Okay? Minus, now let's just deal with v plus 3w. I'll write down what v is. 4, 3, 1, -1, plus, and I need to put that in some sort of yuck.
Okay. That's V plus, and let's go on and do what is 3W. What would that be? Oh, wait, I'm sorry. Yeah, I'm sorry. I was looking at V. Negative 18. Second? 6, you said? Okay, right. I can't hear well. 0, 9. Got it. Okay. Now, 4, negative 2, 10, 0, minus. Now let's add those two vectors that are in the parenthetical expression together. Oh, man. Okay, let's add those two, and what do we get? Negative 14, 9, 1, 8. Okay, now let's subtract those two. Can you do it in your head, or do we need to take a step or two? Okay, what would that be? 18. Negative 11. 9. I couldn't hear what's the last. Negative 8. Sorry. I heard you were saying something, but my ears just would not tune into it. Mostly because I was being distracted by the fact I was afraid I was going to start dripping like crazy. Sorry. All right, let's see what they got. 18, negative 11, 9, negative 8. Perfect. Okay. Let's erase that. I wrote too big. All right. Let's just do the eraser here. All right. I hope I won't need any of that because I'm getting rid of it. I think I will. Just glancing at it, I couldn't see any reason I should. Okay. It said find x using each equation. Here's the B one. 3 times x plus w equal 2u minus v plus x. All right. Yuck. All right. Now, how would you find x in that case? Yes, start with distributing the 3, and what does that give you? 3 is equal to 2u minus v plus x. Now what? Second, subtract x from both sides. That's a legal move. That will give you, oh, what were you going to say? Subtract 3w from both sides. Okay. I'm getting saturated again. Yuck. All right, what does this leave you? 2x to u minus V. All right.
Hate this. Oh, man.
Now what would you do? You would do what?
I said I would solve for the other stuff first, then divide by 2.
Okay, that's a perfectly legitimate way to go. So this would be what? What is our 2u?
2u is 4, -2, 10, and 0.
Yep, we had done that before. And what's your minus v? I'm going to put a plus here. So what is negative v? -4, -3, -1, 1. Yeah. Okay. Now minus 3w. Yuck. Let's go on and do it. That would be a plus what? 18. Wait a minute. You said this ain't -6. I was hearing -2. I said it can't be. Okay, but then I realized I'm not hearing well. Okay, next. 0 and -9. Seems like we had done that one before too at some point. Yeah, and then we're just going to add all those together, and what do you get? 18. -11. 9. -8. Okay. And then to get x. And what would that be? 9. -11 halves. 9 halves. -4. Good. Let's see what they got. 9, -11 halves, 9 halves, and -4. Excellent. Okay. I can't believe I'm not going to make it. So let me go change out again. Okay. I've wasted so much of the time of class today. Now, we've already mentioned the zero vector in Rn, and we already said in the theorem 4.2 is the additive identity in Rn, just like 0 is additive identity in the real number system. Similarly, the vector negative v is called the additive inverse of v. That was over there in number 5 before it was used, but it's still that. Okay. The following theorem summarizes several of the important properties of additive identity and additive inverse in Rn. Okay. So this will be theorem 4.3. And by the way, sorry I took longer than I intended. Stepped out into the hall. A student was waiting for me there, asking when we could get together and do a schedule. I said, well, I'm in class right now. So I gave them the time, said I'd be available. And then I went down the hall. The custodial staff had the restroom blocked, so I had to go all the way down to the other end of the hall to get some toilet tissue. Sorry. All right. So here's theorem 4.3. So let's let V be a vector in Rn. Okay. C is a scalar. These properties are true. First, the additive identity is unique. Now that hardly seems worth saying. That is, if V plus U is equal to V. Yuck. Here we go again. Oh man. So, if V plus U is equal to V, then that implies U has to be the zero vector. No question about it. There can't be two identity elements. There's only one. So if one matches the quantities, it has to be that identity element. Number two. The additive inverse of V is also unique. Additive inverse of V is also unique. Sorry. Is also unique. That is, if V plus U is equal to the zero vector, then that implies that U has to be negative V. There's no way around it. There's no other possibility there. Okay? Now, here's another one we haven't hit on, but it should be pretty obvious. If you think about it. If you take the number 0, multiply it by the vector V, what you're going to wind up with is 0 times V1, comma 0 times V2, comma 0 times V3. All of them are going to become zeros, so that becomes a zero vector. So the scalar 0 multiplied by the vector V, or any vector in n space, is going to give you the zero vector in n space. Okay? And almost seeming like the same stuff for any scalar C that you multiply by the zero vector. Doesn't matter how big or how small or how anything C is, not going to change the zero vector. It's going to stay the zero vector. Okay? And number 5. This is the zero product principle. If C times V is equal to the zero vector, okay, that implies that either C is equal to 0 or V is equal to the zero vector. Okay, C being a scalar, that would be the number 0, or V being the vector, would be the zero vector. Okay? Now, no other option there. Either C0 or the vector V is the zero vector. So 0 is a number, zero vector is a vector. And then number 6. And this should be fairly obvious too. If you do the opposite of the additive inverse of V, then you're going to wind up with V again. So if you negate a negative, you come out with a positive. Okay? Now they have a little blurb here where they do some of the proofs there. I'll let you take a look at those. There is a linear algebra applied at the bottom of the page, which if you've had physics, you probably run into that problem before. So I'll let you read that if you'd like. And we'll start next time with a linear combination of vectors. Sorry if I hadn't had to break at least twice or three times, however many times I did, we would have finished the chapter, I think. So we'll begin next time, or the section, with linear combination of vectors. And homework exercises, do number 1, do either 3 or 5 or both, either 7 or 9 or both, any of the odds 11 through 15, do 17, do any of the odds 19 to 23, do 25 or 27 or both, do 29, do 31, do either 33 or 35 or both, do 37, and stop there. We'll do the rest of those next time. Okay? Sorry that it's been so weird today. So hopefully this will get better.